Yeah. So today we are going to have Hotat Lam from MIT telling us about non-invertible symmetries, condensation, duality defects, and 3+1 dimensions. So Hotat, please go ahead.
Yeah, thank you, Lakshay. So yeah, so as Lakshay said, so today I'm going to talk about non-invertible condensation, duality, and triality defects in 3+1d. So this will be based on two works. So one which appeared last November, and the other one will be appear hopefully this month with this list of authors. So it's Ichu Choi and Shuhan Shao from University of Stony Brook, and Clay Cordova from University of Chicago, and Portion Singh from UCLA. So let me also mention two other papers. So one of them is by this Japanese group, which study specifically duality and condensation defects on ZN lattice gauge theory in 3+1d. And there's another paper by Katie, Omari, and Jen, which discuss also condensation and duality defects in 3+1d. And the approach that they use are slightly different from ours, but we obtain similar results. And also example that they discuss are also complementary to ours. So I understand that Justin has already talked about condensation and duality defects that discussed in this paper. So in my talk, I will try to discuss condensation and duality defects from slightly different perspective that is covered in this paper. And then in the second half of the talk, I will focus more on the triality defects, which will be the main topic of the upcoming paper. So after all this, let me start. So to this audience, I probably don't have to say too much why we care about global symmetries and how important and how useful they are for our study of quantum field theory. But nevertheless, let me just remind you of the basic. So in the modern inclinations, the abstract way to think about global symmetries is to think of them as a set of topological defects in a quantum field theory. So for example, if we have a global symmetry G, we can think of it as characterized by some symmetry defects, which are some codimension-one topological defects inside the quantum field theory. So this symmetry defects in general has three properties. So first of all, it is supported on a codimension-one manifold. So in common practice, we will just take this codimension-one manifolds to be on the space, and then this will just define the usual unitary symmetry operator that acts on the Hilbert space. But since we're dealing with relativistic quantum field theory, we can just consider a more general codimension-one manifold. And this symmetry defect has a property that it is topological in the sense that it is invariant under small deformations of the manifold M. So we can just deform the manifold whatever way we want, as long as we don't cross any local operator. And the third property is that we can talk about fusions of this symmetry defect. So this is what I've drawn here. So imagine that we have two symmetry defects that are placing parallel to each other. We can just collide them because they are topological. We can collide them, and then this will define a new topological symmetry defects for us. And the way the fusion works is just how the group multiplication works, as in this group G. Okay. So after this characterizations of global symmetry using topological defects, there has been a lot of generalizations of the notion of global symmetries in many different directions. So one of them is probably familiar to most of you, which is higher form symmetries. That's simply the idea behind higher form symmetry is to modify the dimensionality of the symmetry defects. And there's another generalizations which is orthogonal to this one, which is called non-invertible symmetries. So the idea behind non-invertible symmetries is instead of modifying the dimensionality of the symmetry defects, we modify the fusion rule of the symmetry defects. So we can consider more general fusions other than a group-like fusions. So let me be more specific. I will be considering non-invertible lines in, let's say, 1+1 dimensions. So generally, topological lines in 1+1d do not always fuse as a group. So the most general way they can fuse is that given a line A and a line B, when we fuse them, we get a bunch of other lines. So we get a linear combinations of lines on the right-hand side. So these linear combinations can involve more than one objects. And because of this, the fusions will not be a group. And also because of this kind of fusions, these lines can in general be non-invertible. So when I say a line is invertible, what I mean is that this line has its inverse which I denote by d minus 1. And when I fuse the line with its inverse, I will just get identity on the right-hand side. And I only get identity. I don't get any other objects on the right-hand side. And in fact, non-invertible topological lines are everywhere in 1+1d. They exist in almost all rational CFT. So for example, if you give me a diagonal rational CFT, I can just find the Verlinde lines in this rational CFTs, and they will define a set of non-invertible topological lines. So the simplest example is of such non-invertible topological lines is the Kramers-Werner duality line in Ising CFT. So Ising CFT has 3 topological lines. So it has the trivial line, and it has the Z2 symmetry line. And the hallmark of a Z2 symmetry line is that if we fuse 2 of them, we'll just get a trivial line. And that the third line that exists is the Kramers-Werner duality line, which I denote by D. So the way this D fused with other topological lines works is as follows. So if we fuse a Z2 symmetry line with a Kramers-Werner duality line, no matter how we fuse it, we always get the Kramers-Werner duality line. But more interestingly, if we fuse 2 Kramers-Werner duality line, we can get 2 objects on the right-hand side. We get an identity line and the Z2 symmetry lines on the right-hand side. So here we see that because of this Kramers-Werner duality line, the fusions is actually non-invertible. And specifically, that means that when I consider this duality lines, I cannot find its inverse. And when I fuse such that I fuse D with its inverse will just give identity. And we can also talk about how this topological lines act on local operators. So for example, this duality lines will map the spin field operator sigma to a non-local disk operator mu, which I've drawn here, so when I bring a sigma across the duality lines, it will become some lines that live on the endpoints of the Z2 symmetry line. So here, because the line maps a local operator to a non-local operator, so it must annihilate the states that corresponds to the spin field operator sigma. So here we see that the actions of the duality line on the Hilbert space, that it's not invertible because it annihilates states. Okay, so here I refer to this line D as the Kramers-Werner duality line. That is because the very existence of this Kramers-Werner duality line implies that the theory has a Kramers-Werner duality. That means that the theory is invariant under gauging a Z2 symmetry. And in fact, the converse is also true. So if the theory is invariant under gauging a Z2 symmetries, the theory will have a non-invertible Kramers-Werner duality line. Okay, so in fact, in recent years, there has been
as a state, isn't sigma getting mapped to mu as a twisted sector into the twisted sector Hilbert space?
Oh no. So how should I say this? So the way to think about this is as follows. So let's imagine that we have the operator sigma inserted at origin, and then we have D wrap around the sigma operator. Okay, so then I can just shrink this D. Then you'll imagine that it becomes some defect operators. But then this defect cannot end anywhere, right? So it only ends on mu, but then what about the other signs? It doesn't end anywhere. So that means that D cannot, D has to analyze the state and annihilate the state.
Okay, thank you.
Okay, so now, right, so I've discussed examples of non-invertible lines in 1+1d. And in fact, in recent years, there has been many advocations that we should think about non-invertible lines in 1+1d as generalizations of ordinary global symmetry. So you may ask, why do you want to do that? It just sounds like words that we can say. So in fact, there are many analogies that we can draw. So for example, we can gauge a non-invertible topological lines. So we can gauge some of them. And the procedure is similar to gauging ordinary global symmetry. And also, this non-invertible topological lines can have generalized anomalies. And this is some abstractions to gauging these non-invertible topological lines. And these generalized anomalies can be used to constrain renormalization group flow. So for example, it has been used to argue deconfinement in masses 1+1d adjoint QCD in this paper. So after I tell you the stories about 1+1d, And you may ask the question is that, can we find non-invertible symmetries in higher dimensions? And how often, how easy can we find them in higher dimensions? So first of all, the answer is yes, that we can always find non-invertible, we can find non-invertible symmetries in higher dimensions. And in fact, they exist in many familiar 3+1d systems. So for example, even in free Maxwell theory, there are non-invertible symmetries. And so in this talk, I will discuss 3 classes of non-invertible defects in 3+1d. And I will demonstrate them in free field, in the free Maxwell theory. So this includes the condensation defect, the duality defects, and the triality defects. Okay, so all of these non-invertible defects that I'm going to describe are closely related to the one-form symmetry in 3+1d. So let me just review or remind you how one-form symmetry in 3+1d works. So first of all, a one-form global symmetry will act on line operator. And in 3+1d, a one-form global symmetry is generated by topological surfaces. So its symmetry defects are topological surfaces. So a canonical example of theories with one-form symmetry is the 3+1d free Maxwell theory. So the theory has a U1 electric one-form symmetry, which shifts the gauge field A by a flat connection. So because we shift the gauge field A by flat connections, the field strengths will be invariant, so the actions will be invariant. So that's why it's a global symmetry to the theory. And the operators that are charged under this electric one-form symmetry are the Wilson lines, or in the free Maxwell theory. So in this talk, I'll be focusing specifically on 3+1d theories with a Z to one-form symmetry. And in the original papers, we also have more general discussions on Z and one-form symmetries. So if you're interested about that, I'll encourage you to look at the paper. So let me start with the condensation defects. So for any 3+1d QFT with a Z to one-form symmetry, we can define condensation defect. And the way it works is that we simply gauge the Z to one-form symmetries along a codimension-one manifold M. So usually when we talk about gauging, we will say that we gauge a symmetry on the whole space. And when we gauge a symmetry on the whole space, that means that we sum over all possible insertions of symmetry defects on that space. But now we are talking about gauging the symmetry along a codimension-one manifold. Then that means that we want to sum over all possible insertions of symmetry defects that wrap around various 2 cycles on this 3 manifold M. So this is what I've written here. So this is given by sum over all possible symmetry defects on the 3 manifold M. But then there's an important coefficient we need to include, which take care of the gauge parameter degrees of freedom. So in fact, this procedure of defining condensation defect is very general. It works in any dimensions. And so if you have a Q-form symmetry, you can just gauge it on a codimension P manifold, as long as P is less than or equals to Q+1. So this procedure of defining condensation defects is introduced in this paper, in this recent paper, and they refer to it as higher gauging. So in fact, condensation defect associated to one-form symmetry in 3+1 dimension is not unique. There are, in fact, multiple condensation defects. And yeah.
May I ask a naive question? Is this an operation on a theory, or is it an operation on a class of defect in a given theory? Like, is it?
Yeah, that's a very good question. So this is not an operation on a theory, because an operation on a theory will means that we gauge the symmetry on the whole space, on the whole space time. But here we only do it in a codimension-one manifold. So this will define some defects, some topological defects for you in the original theory. Okay, so let me continue. So as I said, so there are multiple condensation defects, and the way to think about that is that we can introduce discrete torsions to this gauging. So the way this works is that when we gauge a one-form symmetry along a codimension-one manifold, it is like gauging a zero-form symmetry. So this is because a one-form symmetry is generated by surfaces. And if we insert surfaces on a codimension-one manifold, it is like talking about surfaces on a 2+1d QFT. And the surface in 2+1d will generate a zero-form symmetry instead of a one-form symmetry. So the discrete torsions that we can introduce are essentially the same as the discrete torsions that we can introduce for gauging a zero-form symmetry. So they are just classified by the third group cohomology of Z2, which is given by Z2. So that means that there are two different condensation defects associated to gauging a Z2 from symmetry on a codimension-one manifold. And so one of them is the trivial class, which I discussed before, and the other one is the non-trivial class. And the non-trivial class is characterized by this topological actions, which is given by 1/2 A cup delta A. So here A can be thought of as the Poincare dual of the surface sigma on the manifold N. So if we introduce this discrete torsion to a condensation defect, that just means that we want to introduce a phase factor in sum, and this will modify the sum, and this define the condensation defects that I denote by C1. So the previous defect I denoted by C0. Okay, so now we can talk about fusions involving condensation defects. So what are the objects that will be involved in the fusions? So first of all, we have the condensation defect, which is a three-dimensional object. And then we also have the symmetry defects, or that we start with. So that is that are some surfaces, some topological surfaces that we can talk about. So the fusion algebras that we will consider will involve two-dimensional objects and the three-dimensional objects. So they in general have different dimensionality. But nevertheless, we can still talk about the fusions. And the way this works is as follows. So let's consider a volume defect, a three-dimensional defect, and we place it on some plane. And then we consider another surface defect, which is parallel to this volume defect. So when we fuse them, what we mean is that we want to push this surface defect on the volume defect. And when we do that, this will define for us another volume defect. And specifically, we want to consider the fusions between the condensation defect CK and the symmetry defect eta. So when we fuse eta with CK, this will just modify the sum. And the sum now will be a sum over eta sigma plus sigma prime. And in this sum, we can just pull out an overall factor, which is given by 1 minus 1 to the power KQ. And the remaining sum is nothing but the condensation defect CK. So here we see something interesting. So when we fuse a symmetry defect with a volume defect, we find that the fusion coefficient in general depends on the underlying manifold N. And this also depends on the surfaces sigma. And the way to think about this fusion coefficients is to think of it as some partition functions of an invertible TQFT on the manifold N. So this invertible TQFT has partition functions, which is given by a pure phase. And a way to write the actions is to just use the Poincare dual of the surface sigma in M and write it as A cup delta A. So this invertible TQFT, in fact, describe a 2+1d Z2 symmetry protected topological phases, which we also call SPT phase. So here the slogan is that when we fuse symmetry defects with the condensation defects, the fusion coefficient is in general SPT phase, a partition function of SPT phase. Now using this, we can also talk about fusions between two condensation defects. And in fact, two condensation defects will fuse in a non-invertible way. So for example, we can talk about fusing CK1 with CK2. And the way it works is that we can just resolve CK2 into a sum over symmetry defects. And that we can just fuse the symmetry defects with CK1 one by one. And when we do that, we'll just get CK1, and then we'll get some additional phase. So the additional phase will just combine with the sum in CK2 into these objects. So this will be a sum over surfaces sigma, and the summand will be some phase that depends on the underlying manifold and also depends on sigma. And now we can just use a trick by doing Poincare dual. And then by taking Poincare dual, the surface sigma will due to a Z2 cocycle on the manifold N. And then we can just rewrite this sum into a sum which involve topological actions of this Z2 cocycle on M, which is given by A cup delta A with coefficient K1 plus K2. And this is nothing but the partition functions of a Z2 level K1 plus K2 gauge theory on the manifold N. So here we see that when we fuse two codimension-one defects, the fusion coefficient is in general the partition functions of a TQFT, and in this case, it's a partition function of a Z2 gauge theory. So let me summarize what I have discussed so far about condensation defect. So we can always define condensation defects by gauging Zn one-form global symmetry on codimension-one manifolds. And so here I will state the result using Zn global one-form symmetries just to give you a flavor of how things works beyond Z2 global symmetries. And there are multiple condensation defects we can talk about. They're just they are just different by adding discrete torsions to this sum. And they are labeled by coefficient K, which take values in Zn. And we can talk about the fusions of this condensation defects. And this fusions algebra are in general non-invertible. And the fusion coefficients that appears in this fusion algebras can be thought of as the partition functions of a TQFT. And this TQFT can be invertible, or for example, it can be a Z2 SPT, or it can be non-invertible, like a Z2 gauge theory. So in general, a way to summarize them is that this TQFT will describe a symmetry enriched topological phase, which I call SCT. And a symmetry enriched topological phase is essentially some topological order, some TQFTs, which couples to some background gauge fields, which couples to some symmetry. So the slogan here is that fusion coefficient is the same as partition function of an SCT. And because of this condensation defects, in fact, we can conclude that non-invertible defects are almost everywhere in higher dimensions. So for example, in 3+1d, they exist in almost every 3+1d QFT with a Zn one-form global symmetry, because we can just simply build this condensation defects and there will be non-invertible objects in the theory. Okay, so I tell you about this nice fusions, nice non-invertible fusions about condensation defect, but then you might ask, is there anything that is more interesting that is not made of, that is not like this kind of things that we cook up by building up some objects that just look like lower dimensional objects, or that building from lower dimensional objects that look like higher dimensional objects? So the answer is yes. In fact, I'm going to discuss duality defect and triality defects. And roughly speaking, they can be thought of as the square root of this condensation defect. And when I say square root, oh yeah.
It looks a little bit like extension, right? I have a group which is not a subgroup of the full group. And then when I take the group multiplication, I don't get the elements of that group, but some extra elements as well. So if you take that point of view, then one would say that the condensation defects are not actually defects of the theory, but just a projection. They don't sit as a subgroup of the defects. Or
Yeah. I think that's a correct way to say that. You can think of it as from a point of view of a symmetry enrichment or as you said, as group extensions. Yeah, I think that's a correct way to say things.
And then the coefficients will become standard numbers again if you lift it to the correct group.
That's right. Yeah, that's right. Yeah, that's right. But yeah, so in that sense, you can say this condensation defect is maybe a little bit too trivial for us. So then I'm going to discuss something that is less trivial, which cannot be thought of as like making up from this like lower dimensional objects. Okay. So this will be duality and triality defects. So the idea behind duality and triality defect is that we want to generalize the stories about Chern-Simons duality in 1+1d to higher dimensions. So in 1+1d, we know that if we have a theory that is invariant under gauging, which means that the theory has a Chern-Simons duality, implies that the theory has non-invertible lines. So similar story should work in higher dimensions. So if we can find a 3+1d QFT, which is invariant under gauging a Z2 one-form symmetry, then the theory will have non-invertible defects. And such QFT can exist because in 3+1d, when we gauge a Z2 one-form symmetry, we will get a new Z2 one-form symmetry or a quantum Z2 one-form symmetry. So the symmetry on two sides actually matches. So the way this works is as follows. So when we gauge a one-form symmetry, that means that we want to couple the theory to a dynamical Z2 two-form gauge theory. And in a two-form in a Z2 two-form gauge theory, there exists some topological Wilson surface operators, which are just given by integral of the two-form gauge fields on the surface sigma. And this topological Wilson surface, when you fuse two of them, you just get the trivial surface. So they form a Z2 fusion algebra, and they will generate Z2 quantum one-form symmetries in the gauge theory. Okay, but so now we are instructed to look for theories that are invariant under gauging a Z2 one-form symmetry. But notice that when we gauge symmetries, there are multiple ways to gauge a symmetry, and they are different by adding discrete torsions. So in fact, in 3+1d, if we want to gauge a Z2 one-form symmetry, there are 4 different ways to do this, and they are classified by the force cohomology class on these objects. And this is a Z4 group. So let me now discuss a little bit more about this gauging operations. So in fact, on the space of 3+1d QFTs, with the Z2 one-form symmetry, we can define an actions, SL2 Z4 actions in general, pointed out by this paper. And the idea is follows. So we can define 2 operations, S and T operations. So the S operations is just gauging a symmetry. So when I say gauging a symmetry, I mean that I want to sum over the partition functions in the presence of all possible Z2 two-form gauge fields. And in the sum, I'm allowed to introduce a phase which tells us how the background gauge fields B is coupled to the quantum Z2 one-form symmetry. And the T operation is the operation that we just stack on top of the original theory, another invertible field theory, which depends on the background two-form gauge fields for the one-form symmetry. So this invertible field theory can be thought of as Z2 one-form SPT protected by this Z2 one-form symmetry. And this S and T operations obey the following relations. So if we do the S operation twice, we'll just get back to the original theory. So this statement is nothing but if we gauge the Z2 quantum one-form symmetries, we'll just recover the original theory. And another relation is that when we do the ST operation 3 times, we'll also get back the original theory, but up to a phase. And that phase is given by invertible field theory denoted by Y. And the third relation is that if we do the T operation 4 times, we'll just get back to the original theory. So this is the statement that the torsion class or the Z2 one-form SPT are classified by a Z4 class. So if we stack 4 Z2 one-form SPTs, we'll just get a trivial SPT. So now let me say a little bit more about this this invertible field theory Y. So Y is an invertible field theory, and it can be realized as a Z2 two-form gauge theory. So its partition function can be written as the following form. So this is the Z2 two-form gauge theory with topological actions that is given by I pi over 2 B cup B. So from this realizations, then it's not hard to imagine that something like ST cube equals to Y can be true. That is because this two-form gauge fields B can be thought of as coming from this ST cube operations. So this theory is an invertible field theory. So that means that if we put it on closed manifold, its partition function will just be a phase that depends on the manifold. But more generally, we can put this Z2 two-form gauge theory on an open manifold. And if we do that, we have to specify the boundary conditions. And we can just pick the Dirichlet boundary conditions for the two-form gauge field B. And if we do that, we will find that on the boundary of this open manifold, there's a U1 level 2 Chern-Simons theories on the boundary. Okay, and this fact that there's a U1 level 2 Chern-Simons theory on the boundary will be extremely useful when I discuss the fusion rule involving triality defect. So now let me discuss duality and triality defects. So the idea is that we want to look for theories that are invariant under gauging. So if we have a theory that is invariant under the S gauging of a Z2 1-form symmetry, the theory will have duality defects. The reason why we call it duality defect is because S squared equals to 1. And if we find a theory that is invariant under ST gauging of a Z2 1-form symmetry, we'll find this theory will have triality defect. And the reason why we call it triality defect is follows from the fact that ST cubed, if you do ST 3 times, you will just get back the original theory up to an invertible phase given by Y. Okay, so these are the conditions for the theories that have duality and triality defects. Okay, so suppose these conditions are satisfied, how can we define duality and triality defect? So the way we define them is very simple. So suppose the condition is satisfied, then we can just define the duality or triality defects by gauging the Z2 1-form symmetry in half of the space-time. And when we gauge the symmetry, we have to specify the boundary conditions. And the boundary conditions we specified will be the Dirichlet boundary condition for the Z2 2-form gauge field B. Okay, so let me demonstrate this. So for example, let's consider duality defect. So a duality defect can be thought of as an interface that separates the theory Q and the theory SQ, which is a theory after doing an S operation. And in general, this will define just an interface between two theories. But if the theory Q and SQ are the same, then this will become a topological defects in a single theory. And we can use the fact that S squared, we can use the fact that S squared equals to 1. And then we can just, we can use the fact that the series is invariant under the S operations. Then we can just do S inverse on both sides. Then on the right-hand side, we'll just recover the original theory Q. And on the left-hand side, it will be applying S inverse operations on the theory Q. So now the picture will be slightly different. So the original picture will be doing a gauging on the right-hand side, but now on the picture that I've drawn here, this will now becomes doing the gauging on the left-hand side of the duality defect. So similarly, we can define triality defect as an interface between the theory Q and the theory that is obtained by doing an ST gauging. And using symmetry, we can just apply ST inverse on both sides. And now we can also think of the triality defects as an interface that separate ST inverse Q and Q. So, right. So now we have this duality and triality defect. So in fact, this duality and triality defects are topological defects. So the reason why they are topological simply follows from the fact that the Z2 two-form gauge theories are flat. So if we impose Dirichlet boundary conditions on some, let's say some interface, we can just change this interface. And because the gauge fields B are flat, changing the interface will not change this boundary condition. So similar to this duality defect D and T, we can also define their orientation reversal, which will be important for the discussion later. So the way this works is as follows. So let's consider, for example, the orientation reversal of D, which I denote by D bar. So if we take an orientation reversal of these pictures, what we will do is that we just rotate the pictures. And when we rotate the pictures, now we'll find that D bar will now separate SQ, which live on the left-hand side of the defects, and Q, which live on the right-hand side of the defect. So orientation reversal of D and T is simply just rotating the picture that I've drawn here. Okay, now after defining the duality and triality defects and also their orientation reversal, we can now talk about fusion rules. So I will be focusing specifically on—
Can I ask a question?
Yes.
Suppose Q is invariant under ST, and then does it mean that Q is invariant under stacking invertible theory Y?
That's right. That's right. Yeah, that's right.
But if the partition function of Y is not identity, so the partition function of Q should vanish, right?
Yeah. Yeah, that's right. Yeah, that's right. Correct. So yeah, that's right. Yeah. In fact, something like this will be important later when I discuss some consistency of these fusions. Yeah.
Okay, but because ST cube is Y, so do you interpret it as the theory is invariant under ST cube? Because doing ST cube does not map the theory back to itself, but it only...
That's right. So yeah. Let me say this. So as you said, the theory will be invariant under stacking Y, the invertible field theory. And then you can ask how can this work? So the way this works is that whenever you have a manifold where Y is non-zero, then Q, the partition function of Q, has to be 0. Does that make sense?
Yeah, that makes sense. But I'm just wondering, so you interpret this as Q being invariant under ST doing 3 times.
That's right. Yeah, that's right. Yes.
Oh, okay.
Yes.
Thanks.
Yeah. Okay. Good. So now let me talk about fusion rules, and I'll only talk about fusion rules involving triality defects because they are more non-trivial, and the fusion rule for duality defects can be just derived using similar methods. Okay, now let's talk about triality fusion rule. So we can talk about fusions between T bar and T. So first of all, a T bar is an interface that separates Q and ST inverse Q. And T is an interface that separates ST inverse Q and Q. So when we discuss fusion of T bar and T, this will divide the region into divide the space into 3 regions. So on the left hand side is Q, in the intermediate region is ST inverse Q, and on the right hand side is Q. Okay. And now we can use the fact that ST inverse is just given by T inverse S. And because doing a T inverse after doing an S gauging only affects the coupling to background gauge field. So then we can just ignore about this T inverse. So then fusing T bar and T is just like doing an S gauging in a thin slab that is sandwiched between T bar and T. And we know that doing an S gauging of a Z21 from symmetry is nothing but summing over symmetry defects on this 3 manifold. And so then this is nothing but the condensation defect that I defined before. So this means that when we fuse T bar with T, we'll get the condensation defect. So we can also talk about the opposite fusions. We can talk about how T and T bar are fused. So T is an interface that separates Q and STQ, and T bar is an interface that separates STQ and Q. Okay. And now, as before, we can just interpret the fusion between T and T bar as doing an ST gauging now within this thin slab sandwich between T and T bar. So doing an ST gauging will be the same as summing over symmetry defects. But then because I introduced a discrete torsion gaugings, so this will introduce a phase in sum. And this phase will just be -1 to the power Q. So the sum will be -1 to the power Q and sum over all possible insertions of symmetry defects. And this is nothing but the condensation defects, C1 that I have defined before. So here we see that the fusion is generally non-commutative. So when we fuse, before we fuse T bar with T, we get C0. But here we fuse T and T bar in the opposite way, we get C1 instead. So we get a non-commutative fusion. So another things we can talk about is the fusion between T and T. So when we fuse T and T, we can think of it as follows. So this will be 2 interfaces that separate 3 regions. So on the left-hand side, we have Q. In the middle, we have STQ. On the right-hand side, we have ST squared Q. Okay, so when we collide them, we can just ignore about the middle regions. And then we can ask what happens to the right-hand side. So on the right-hand side, we can use the fact that ST cubed equals to Y and replace ST squared by Y ST inverse Q, okay? So when we do that, we recognize that this Y is just an invertible field theory, and it is a decoupled invertible field theory from ST inverse Q. And now I can just use the fact that I mentioned before. So on the boundary of Y, there's a U1 level 2 Chern-Simons theory. So then I can conclude, I can make the following conclusion. So when I fuse T and T, I will get a decoupled U1 level 2 Chern-Simons theory on the domain wall, and the interface that separates Q and ST inverse Q. And the interface that separates Q and ST inverse Q is nothing but T bar. So then this gives us the interesting fusion that T times T, T fused with T will give us T bar with a fusion coefficient that is given by the partition function of a U1 level 2 Chern-Simons theory. And now you can just apply this this operation twice, then you will get that when we fuse T 3 times, we'll just get the condensation defect C0 and with a coefficient U1 level 2. So this is similar to you can think of it as an analogy of the relation that ST cube equals to Y. Okay. So now we can also talk about fusion rules that involve the triality defects and the symmetry defects. So symmetry defects is a surface, and triality defects is three-dimensional objects. So when we fuse them, that just means that we want to push the symmetry defects on the triality defects. So we can let's consider first fusing T with eta. So eta now lives on the right-hand side of T. So I can use the fact that T separates a theory Q and STQ. Then I can just identify the symmetry defect on the right-hand side as the symmetry defect associated with the Z2 one-form quantum symmetry. And that is nothing but the Wilson surface operator given by the integral of B. And now I'm going to push the symmetry defects to the duality, to a triality defect. When I do that, notice that I impose the Dirichlet boundary condition, B equals to 0 on the triality defect. And because of this boundary conditions, when I do this fusions, the symmetry defect will just be set to trivial or set to identity. So that means that when I fuse triality defects with a symmetry defect, I'll just get triality defect back. But then I can also talk about opposite fusions. So I can fuse A dot with T from the left-hand side. And again, the fusion will be non-commutative. And the way to see this is that on the left-hand side, the symmetry defect is not just given by the Wilson surface. It also has an additional phase. And the reason why there's an additional phase is that on the left-hand side, I'm using the description, I'm using another descriptions of the triality defect T. So on the left-hand side, it's given by T inverse SQ. So this means that I need to do a gauging first, and then I stack on top of this another SPT. And because of this stacking of SPT, this will modify what we mean by symmetry defects. And this will introduce this phase given by exponential I pi over 2 and the Poincare dual sigma square. So now we can ask what happens when we push this symmetry defects to the triality defects. So the first term will just vanish because of the boundary condition where we set because of the Dirichlet boundary conditions where we set B to be 0. But the second term will now give you a non-trivial phase, and this non-trivial phase will reduce to -1 to the power q. So this gives you eta times T equals to -1 to the power q T. So let me summarize the fusion rules that involve triality defects. So for any 3+1d QFT that is invariant under ST gauging, Z2 one-form global symmetry, we'll find non-invertible triality defects, or we can define non-invertible triality defects in this theory. And we can talk about fusions, and the fusions will involve triality defect, the orientation reversal of the triality defects, and also the symmetry defect, which is a surface operator, and various condensation defect. And some lesson that we learn from this fusion rule is that the fusion is generally non-commutative. This is, for example, when we fuse T bar and T in opposite order, we'll get different answer. And also the fusion coefficient that we see here is generally the partition function of an SCT. So for example, it can be -1 to the Q, which is an invertible TQFT, or it can be the partition function of a U1 level 2 Chern-Simons theory. So with this triality fusion rule, we can also check various associativity. And so, for example, we can consider the fusion between T times T and times eta. So there are two ways to fuse them. So first of all, we can fuse T with eta. So when we fuse T with eta, we can just use this triality fusion rule. So we'll just get T. Then we can fuse T with T again. We'll just get U1 level 2 times T bar. So another way to fuse it is to fuse T with T first. And this will give us U1 level 2 T bar. But then we can fuse T bar with eta. But when we fuse T bar with eta, we'll get an additional phase, -1 to the power q. So here we seem to get a puzzle. So there are two equivalent ways to fuse T with T and with eta, but then they seem to give different answer. So but the resolution is as follows. So in fact, U1 level 2 is invariant under stacking an SPT that is given by -1 to the power q. So this is related to the question that Yingqin is asking. So Yingqin is asking that whether the theory is invariant under stacking an invertible field theory. So the question he asked is about the 3+1 dimensional theory. And here, this is the 2+1 dimensional versions of that 3+1 dimensional properties. So a way to prove this relations is to just write down everything explicitly. So a U1 level 2 Chern-Simons theory has a Lagrangian that is given by 2/4 pi ADA. So A is a dynamical gauge field. And the SPT -1 to the power q can just be given by these actions. So the first term, so I'm trying to embed a Z2 gauge field in a U1 gauge field. So the first term simply just tells us that, so here C is a dynamical gauge field and A is a background gauge field. So the equation of motion of C simply tells us that A is a Z2 gauge field. So this just constrains the U1 gauge field to be a Z2 gauge field. And then the second term is the topological actions for the Z2 gauge field. And if we reduce it to Z2 gauge fields, this just gives us -1 to the power q. Okay. And then we can just combine terms and rewrite these actions or these combinations into the right-hand side. So the first term is again a U1 level 2 Chern-Simons theory. And the second term is nothing but a Lagrange multiplier that constrains the gauge field A to be a Z2 gauge field. So we can just ignore about it. So here we prove the relation that a U1 level 2 Chern-Simons theory is invariant under stacking a -1 to the power q SPT. So another way to state, so a consequence of this relation is that whenever we have a manifold where -1 to the power q is non-zero, then the partition function of U1 level 2 has to vanish in that manifold. Okay. Okay, so I've derived the triality fusion. Yeah.
Can I? So the associativity can in principle be not true, right? So it does not have to be true. If there's so associativity is violated, then there can be anomaly.
Oh, that's what you mean. Okay, yeah. But let me think about that. But here I think I'm talking about things at the level of fusions. I'm not talking about junctions and things like that. So I think, like for example, I think maybe this is not correct, but I think that when the fusion is not associative, this is only true in quantum mechanics. Only in that case that implies anomaly, right? Like for example, in 1+1d, the anomaly is encoded in the F symbol. It's not in the fusion rules. So I think in higher dimension, it is usually expected to be associated with the fusion rule. Does that make sense?
Oh, yes. Yes.
Yeah. But maybe there are some things that are not associated, but we might be just limiting ourselves to in this case. Yeah.
Yes. Thanks.
Yeah. Okay. Okay, so I've derived the triality fusion rule for you, and let me just quickly flash how duality fusion rule works. So in any 3+1d QFT that is invariant under S gauging a Z2 from symmetry, we can define non-invertible duality defects, and this is the fusion rule. So when we fuse eta with D, the fusion will be commutative, and then we will always get D. And when we fuse D with D bar, we just get the condensation defect. So in some sense, the duality, the fusion of duality defects are like direct analog of the Kramers-Werner duality fusions. And triality defects is a little bit like generalizations of this fusion rules. Okay, so now I've discussed a lot of abstract operations or abstract way to define this non-invertible defects. Let me talk about concrete examples. So I will discuss Maxwell theory, a 3+1d Maxwell theory specifically. So a 3+1d Maxwell theory has a complex coupling, which is given by tau, and it is given by theta over 2 pi plus 2 pi I over E squared. So a 3+1d Maxwell theory enjoys an electromagnetic duality, or it's also called S duality, that maps the theory from tau parameter at tau to the theory at minus 1 over tau. And as I said before, a 3+1d Maxwell theory has a U1 electric one from symmetry, but we will just take the Z2 subgroup of it to define the S and T actions. So because of S duality, the theory at tau equals to 2i is actually invariant under S gauging. The theory at tau equals to 2 exponential 2 pi I over 3 is also invariant under ST gauging. So let me just explain how this works for tau equals to 2i. So for tau equals to 2i, if we do a S gauging for the electric Z2 from symmetry, this will just make the gauge fields. This will just put a factor of 1/2 in front of the gauge field, and because the action is quadratic, so the tau parameter will just divide by 2 squared, and now it will map tau equals to 2i to I over 2. And because of S duality, tau equals to half I is the same as tau equals to 2i, so we recover the original theory. So here we see that because of S duality, we can find points where Maxwell's theory is invariant under gauging, specifically S gauging the electric Z2 from symmetry. And at tau equals to 2i, we can realize the duality defect as follows. So let's imagine the duality defects divides the space into 2 parts. So on the left-hand side, we have A left, we have gauge field AL, and on the right-hand side, we have gauge field AR. And on the domain, on the duality defects, they will just be coupled. And the way they are coupled is through a Chern-Simons term, a diagonal Chern-Simons term with coefficient 2. So the reason why this describes duality defects can be seen by looking at equations of motions. So let's analyze the equation of motions. So let's vary this whole actions with respect to A left. So when I vary respect to A left, I will get terms that is supported on, that only lives on the domain wall, or only lives on the duality defects. And this is given by I times FR, which is the field strength of AR. But notice that A left is also participated in the bulk actions. And when we vary respect to bulk actions, we need to do integration by part. When we do integration by part, there will be additional contributions on the domain walls that come from this bulk actions. And the additional contributions will be star F left. So the equation of motion of A left on the domain wall tells us that star F left equals to IFR. So this relates the field strength from the left-hand side with the field strength from the right-hand side. So similarly, there's another equation of motions from AR one can derive. And then these two equations, in fact, have the same content. They give the same equality. And a way to understand this relation between F left and F right is as follows. So we can first gauge the symmetry. And when we gauge the symmetry, the new field strength will be twice of the original field strength. And then we apply S duality. And when we apply S duality, we'll just map the field strength to star F right. And this is essentially what this equation of motions tells us. So using similar tricks, we can also write down a way to realize the triality defects. So triality defects will be realized by also a Chern-Simons coupling or world volume, which has the following world volume Lagrangian. So other than the diagonal coupling that couples A left and A right, there's also a self Chern-Simons term one need to introduce, which involves A left. So it's A left wedge with dA left with coefficient 2i over 4pi. So in the language of this world volume Lagrangians, we can also easily define the orientation reversal of T. So the orientation reversal of T is T bar, and this world volume Lagrangians can just be obtained by from T by doing the rotations on this figure that I've drawn here. So when I do a rotations, first of all, A left and A right have to swap, but then when I do a rotation, I also need to change the orientations on the domain wall. And when I do that, they will introduce a minus sign. And to summarize, the world volume Lagrangians of T bar will just be given by this terms. So it has a diagonal Chern-Simons term with coefficient -2. It has an off-diagonal Chern-Simons term with a coefficient -2, and a diagonal Chern-Simons term now involve A right with coefficient -2. Okay, so now using this explicit world volume Lagrangians, we can talk about fusions. We can use them to explicitly compute the fusions of this triality defects. So for example, so the way this works is as follows. So now let's consider two defects. So they will separate the space-time into 3 regions. So the left regions, the intermediate regions, and the right regions. So each of them have their own gauge fields: A left, AL, AI, and AR. So when we fuse 2 defects, we will collide them. So when we collide them, we'll just shrink the intermediate regions and then make it disappear. And as a result, this will reduce or restrict the bulk gauge fields AI to a 2+1d U1 gauge fields that only lives on the domain wall. And so, for example, we can use it to derive the fusion rules involving T and T. So when we fuse T and T, the world volume Lagrangian is given by 2 terms. So one of them is the Lagrangians of T, which depends on A left and AI, and the other is the Lagrangian also of T, which depends on AI and AR. So after writing in the Lagrangians, we can just combine terms. And when we combine terms, we'll find that there's a decoupled U1 level N Chern-Simons theory that we can pull out. And then the remaining things can be just organized as T bar. So this is just the orientation reversal of the Lagrangians of T. So here we see that using this explicit Lagrangians, we can derive the fusion rules. And we recover the fact that this fusion coefficient is a decoupled U1 level N Chern-Simons theory. So here I will just give you the taste of how things works. In general, this can just works for both duality and triality defects, and we can also use it to derive the fusion between symmetry defects and the duality and triality defect. Okay, so here I have only discussed the example of Maxwell theory, which is a free theory. So in fact, duality and triality defects exist in many other familiar 3+1d systems, and including some interacting ones. So for example, they can exist in Yang-Mills theory with orthogonal gauge group, and they can also exist in n equals to 1 supersymmetric Yang-Mills theory, and n equals to 2 supersymmetric Yang-Mills theory, and also Zn lattice gauge theory. Okay, so after I telling you all this like fusions or interesting fusion of non-invertible symmetry defects, you may ask, is there any use of this non-invertible symmetry? Can we use them to do something? So for example, one thing we can use them to do is that we can use them to constrain renormalization group flow. So this will be similar to what the Toffel anomaly of a global symmetry does. So usually if we have a Toffel anomaly of a global symmetry, this what tells you that in the IR, the theory cannot flow to a trivially gap phase. So we actually prove a theorem which have a similar content. So the idea is that we have a 3+1d bosonic QFT that is invariant under gauging a Zn1 from symmetry with even n. And if this is true, then the theory cannot flow to a trivially confining gap phase. So when I say a trivially confining gap phase, what I mean is that, so confining specifically means that the Zn one-form global symmetry is preserved in the IR. And when I say it's a trivially confining gap phase, this means that the theory can be thought of as a Zn one-form SPT. So it's an invertible field theory, which can depend on the background gauge fields for the Zn one-form global symmetry. So notice that if a 3+1d theory is invariant under gauging a Zn one-form symmetry, then the theory will have a duality defect. So this statement can be rephrased as the existence of duality defects for even n prevents the theory from flowing to a trivially confining gap phase. So as an applications, we can prove that a Zn lattice gauge theory with even n cannot be trivially gapped at the self-deal point. And this is consistent with the common belief or the common law. So usually people expect that the Zn lattice gauge theory will go through a phase transition at the self-duality point, or might flow to a U1 gauge theory, which is a deconfined theory, deconfined gapless theory at low energy. So in the paper, we have also proven similar constraints for triality defects and also for fermionic QFTs and for odd n. So here I'm only stated for even n and bosonic QFT just to make the theorem simpler to state. Let me just quickly sketch how the proof works. So this will be rather brief. So as I said, a trivially confining gap phase implies that the theory is just a Zn one from SPT. And in fact, Zn one from SPT are all classified, and they are just given by the force cohomology on this space, and which is a Z2n group. And explicitly, they can be written as these actions. So this is a B cup B, and with coefficient 2 pi I P over 2n. So here P labels the Zn or parameterize the Zn one from SPT, and this takes 2n values. So we can just gauge this SPT. So if we gauge it, we will find we'll get this new actions. So our idea, so the idea behind all this behind this theorem is that if we can prove that there's there are no Zn1 from SPT that is invariant under gauging symmetries, then the theory cannot flow to a trivially confining gap phase. So for the theory to be invariant under gaugings, we want that after gauging the SPT, we obtained also an invertible field theory. We don't want it to be a non-invertible TQFTs. So specifically, that means that we want P and N to be coprime. And if P and N is coprime, we can just integrate our B. And when we integrate our B, we'll also obtain Zn1 from SPT, but now with a coefficient minus P inverse of P. So inverse of P is just an inverse of P in a Z2 in a Zn field. And the statement that this Zn1 from SPT is invariant under gauging just means that P equals to minus P inverse mod 2n. So that means that P squared equals to minus 1 mod 2n. And in fact, now this just becomes a number theoretic questions. Is it possible that, so given the n, is there any solutions to these equations? So in fact, if n is even, there are no such solutions. So when n is even, we cannot find a number in a Zn field, in a Z2n field, such that when we square it, we get a minus 1. So this concludes the proof. This tells us that there are no Zn1 from SPT that is invariant under gauging. And as a result, when n is even, and as a result, if we find a 3+1d bosonic QFT that is invariant under gauging a Zn1 from symmetry with even n, the theory cannot flow to a trivially confining gap phase. Okay, so just to summarize, let me conclude. So a global symmetry can be characterized by topological symmetry defects. And generally, the fusions of these symmetry defects can be non-invertible. And non-invertible symmetry defects just define for us a generalized global symmetry, which we call them non-invertible symmetry. And non-invertible symmetries are ubiquitous in 1+1d, and they are also very useful in study renormalization group flow. And in this talk, we show that they also exist in many familiar higher dimensional systems. For example, we discussed condensation, duality, triality defects in 3+1d free Maxwell theory. And they also exist in many other interacting theories, which I didn't discuss in the talk. And the fusions of this non-invariable defects in higher dimensions are quite interesting. So for example, the fusion coefficients in this fusion algebra in general is some partition functions of a TQFT, or more generally, a partition function of an SCT phase. So for example, it can be an SPT phase given by -1 to the power q, or some TQFT like Zn gauge theory or U1 level and Chern-Simons theory. And these non-invertible symmetries are very useful. They can be used to constrain the renormalization group flow that is in the same flavor as a toponymy of a global symmetry. Okay, so that's everything I want to say. So thank you so much for listening.
Yeah, let's thank Hotat for this interesting talk. Are there any questions? Okay, if there are no questions, I will stop the recording and then we can have a free discussion.